All right, so in this example, we are going to apply our understanding of the disk method into finding the volume of a solid that is generated by rotating a region. Okay, and so let's switch over to the wording of the problem on the computer station here. All right, so here we are at the wording description of our problem right here. So it says, the problem says, find the volume of the solid that is obtained by rotating the region bounded by. So here we have a region, and let's look at the four graphs that define or that bound our region. And then think about it. Once we have seen the graph and seen our region then that created by these four graphs right here, we will be rotating that region about the x-axis. Okay, and so I'm going to clear out my highlights again, and let's one by one. I'm going to switch between my my lecture notes here on the computer screen and the graphing calculator. All right, so here we go. The y equals 8x squared right here. So with decimals on my graphing calculator that I'm using, here's the graph. All right, so this is the graph for y equals 8x squared. Okay, and just like how I explained in the general lecture, then general discussion lecture, then we don't have to worry about how the curve given here is being expressed. I mean, currently in the problem, it's worded as y equals 8x squared, but that's just, we only need to see that as an equation that gives us this graph right here. Okay, so that's one graph. Now I'm going to switch back again to the lecture note to find out the other graphs that we're looking at. So the next one we're looking at is how about x equals 0. So this graph x equals 0 is nothing but just the y-axis. Okay, so that is the y-axis on our graphing space right here. So we know the area has to be, the region has to be between this and the y-axis, between the graph and the y-axis. Okay, the graph and the y-axis, the graph and the y-axis. So we are still we are still not finished with the complete description. So the area is still, the region is still a little unclear right here. Okay, so now again back on the wording description, then we have the other two graphs. So now allow me to bring them all up instantly right here. So y equals 3 is a horizontal line, y equals 3, and y equals 1 is another horizontal line. So we have these two horizontal lines. So now that means on decimals right here, okay, in my graphing calculator, it allowed me to graph these. So that's the curve, that's the x-axis. I mean, this is the graph, y equals 8x squared. This is the y-axis that we already knew. And so this is the two lines, y equals 3, and this is y equals 1 right here. All right, and so that means here we are, it is now clear that the region we're shading is to the right-hand side, as you're seeing that in the picture over here, to the right-hand side of our y-axis. So it's this region right here. So allow me to hide away the curve right here. I'm not going to take the complete graph here. I'm only going to take the part of the graph that set the boundary for this region. And so here's our region. Okay, it's the region that's being bounded between these two lines in black and the y-axis and the curve itself right here, and part of the curve. And now I'm going to switch to just to the part where we restrict the curve right here. All right, so I'm going to restrict down the curve, and so that is now our final sketched region. And so again, I mentioned this in the video lecture, but even though the problem does not specifically ask for sketching the region, it is always a highly recommended habit to sketch the region. And then once we've had the region sketch, we're going to start triggering up our imagination, pushing out our imagination so that we can imagine how we rotate that region. Okay, and so now again, back on the lecture note right here, that in the wording description of mine, and once we see that once we have seen and observed our sketch region, now we're going to take that region and rotate that about the y-axis. Okay, so here we want, so the rotation axis in our problem here is the y-axis. Okay, so let's have a look at that to see what the rotation is like with decimals here. So once again, on decimals, okay, then here on the decimal, this shaded region is here. We're going to be rotating that but around the y-axis this time. Okay, and so sadly I don't have a template created for rotating a 3D template to illustrate the idea about rotating this region around the y-axis. So I'm going to have to switch to a different program with GeoGebra right here. Okay, so this same region right here using GeoGebra, and now with GeoGebra we can see that that region is between this line right here and that line. So this is y equals 3, y equals 1, okay, and then the region, this is the y-axis in green right here, and the curve, our restricted curve, is only between here, this portion in blue right there. Okay, and so now once we have had the picture of the region, so now let's look at the rotation. So with GeoGebra here, then I can go ahead and rotate that. So that portion in blue here, let's go ahead and observe the rotation. And actually, let me move the graph a little bit. All right, so I'm going to move the graph to a place where we can see the rotation even more easily. Okay, so now here's how I'm rotating it. That blue curve is going to be rotate, and once again the rotation orientation does not matter, so I'm making a complete 360-degree rotation. All right, so now we have generated for ourselves a picture that looks like a cup. Okay, all right, so and the cup is currently pointing away to that, but the cup here has a flat bottom and a flat top right here, but kind of like a little bit bent in the mid body of it. All right, so that's the idea. That's the idea of the solid that we're creating. So allow me to make another hand sketch version. Okay, another hand sketch version on the board right here, and we're gonna once again dive into it and dissect the information one by one right here, and break down the information one by one. So, and of course, please forgive me that my hand sketch cannot be as precise as the one being shown with either decimals or GeoGebra over here. So the curve we have mainly is this, and the region is between y equals 1 and y equals 3. Okay, so y equals 1 and y equals 3. So this is the region that we're looking at. Okay, that I'm shading with the kind of slanted line right there. All right, so now, and once again, we know that we're going to take that region and rotate that around the y-axis. So this time, now I just realized that I put I put the graph a little bit too far up. Okay, so it's going to be a little hard for me to draw my eyes right here. So, but the rotation axis is the y-axis. So we place the eye looking straight down. So the eye is looking straight down on that. All right, so now again, just like how I was explaining this concept in at the end of the general discussion lecture, then with this region, and here we already knew that our rotation axis is this y-axis right here, then we can, for those people who are not so sure about your own visual sense, and then I deliver this advice right here at the end of my video lecture for the general discussion right here. But think about if we draw from where we have the boundary here and draw a stripe perpendicular down to draw that stripe from the boundary down to the rotation axis. Okay, the stripe here we're drawing from the boundary of the region here, the outer boundary of the region, and draw that all the way to reach and stop at the rotation axis. Then along its way right here, of course, we already learned through the lecture, to the general discussion, that the stripe we doing here should be perpendicular, should be always perpendicular with the rotation axis. But see, in the way where throughout the entire stripe right here, it did not cross as the stripe is going through the region, the stripe does not cross any other boundary aside from this one right here. Okay, and so as a matter of fact, the stripe did not even cross this boundary. It only starts at this boundary and stop at the rotation axis, but does not cross any other boundary at all. And that's one way that tell us, that rings a bell for us, that when we're rotating this, it's going to give us a disc picture as our eyes is looking down. Okay, so it's only an advice for me for whoever doing the problem that feels the not so confident with your visual sense, then you know, you can look at that thing right there and tell so that you can plan ahead that it will be a disk method. Okay, and so I'm trying to deliver every single different experience like that. So to help students and viewers of mine to be successful at this method right here, and we call it, again, it's a disk method. Okay, and each disk here is a cross section. So each cross section, or another way of saying it, each cross section appears to be a disk. All right, and so now in that way, again, now we ring that bell. We rang that bell that the method we are doing here is a disk method. So there is a formula that's commonly given in many standard calculus textbooks. But again, throughout my general discussion lecture, I generally introduce a one fundamental concept, and I highly recommend that students of mine or viewers learning from this lesson to catch the fundamental here, that the work we do in here is accumulation. So we're accumulating at any cross section. We're first going to find the cross section area, and then of course the cross section here is a disk. So once we found the cross section area, then we're going to multiply the cross section area here with the thickness. Okay, and I have explained all of this, each of these components back in a general discussion right here. So in the way how I'm looking at my disk is being placed like this, and the y-axis or the rotation axis is pointing upward, and our eyes is looking down to that, and so each disk right here has a thickness. Okay, and so in the way how we place our disk, then the thickness here has to be the change in y value. So we call it, it's a dy right here. Okay, so now, and then once we've had each one of this product here is giving us the volume of one infinitesimally thin disk. And so in that way, now we are going to be accumulating all the disks here, all the disk volumes here from a start, okay, to an end right here. So now, clearly speaking, once we have rotated our region here, then the start is from the bottom, and in this particular picture, the start is from bottom up. Okay, and that's how we're creating our picture right there. Okay, so from start to end, this is the only fundamental that I want anyone to catch it there, because once you've had that fundamental, it will drive and become different formula. Okay, and so now, again, I have introduced my own experience for doing these problems back in the general lecture. So here, we're going to start out by finding the thickness first. The thickness for each disk in this way right here, as I have explained earlier and already erased the thickness in each disk here, in the way how we place each of our disks. So again, just like how I already explained in the general lecture, every single thing that comes out is a consequence of how we picked it, how we extract out the information from the description of the problem. The description of the problem already gave us the way how it is for our solid. So all we do is we extract that information, and so having the thickness here as a dy is just a consequence of that. So in the way it is, thickness has to be dy, because our stripe that once we're rotating it, create the thickness of the disk. That thickness now has to be a dy, the infinitesimally thin or small change in y. Okay, and now after thickness, we are in the next step here, we are going to derive or find out a formula that regulate our cross-section area, okay, or a general formula for our cross-section area. Okay, and then also, just like how I was doing this practice back in the general lecture, then I'm going to, as we're extracting further and further information, I'm going to also partially evolve our formula. So our formula here came straight out from the fundamental. So thickness we already found to be dy, so the integral now evolves to become, so it's accumulation. We still haven't found cross-section yet, so I'm leaving it here empty for now, or leaving that here as a general description. Okay, cross-section area, but now multiply with dy. All right, and we still don't know where the start is. We will get to that later. We'll get to that ending later. But at least now we know thickness is dy, so that dy differential is here. All right, so now once again think back of how I explained the way how the d expression here in an integral has to be consistent with the function that comes with that, then now it makes perfect sense for us that we have to write the cross-section area here as a function of y, you see, because the variable here is a y, indicated by the dy. Okay, and so now, so we know that area of any circle, see, we place our eyes here looking down view, we have a disk on, right when we're looking down right here. So in the end it's a disk, it's a circle, so area of any circle is pi r squared. But now in the way how the picture looks, then the radius of the circle is going to be that distance that's going from the center of the rotation out to reach the outer, from the center to reach the outer boundary of our region right there, the outer boundary of our region. And so in that way, look at the way how the stripe is, then we have to express that. So it looks like we have to express this curve as a function in terms of y right here. We have to express that height right here as the output of a function in terms of y, because at any different y value we have a different height output that's being long or being short depending on where we put our stripe at. Okay, so in that way, but see, so in this problem, sadly our equation initially came out as a function of x. It was given from the problem y equals 8x squared. So now we can use a little algebra right here to re-express this equation in terms of y. So we can divide both sides by 8. Okay, so that gives me y over 8 equals x squared. And then to solve for x as an expression in terms of y, remember we want to express the same curve but as a function of y. Okay, so I'm on my way. So the simple algebra work here is to solve from this initial equation we were given. We are going to solve that for x. So that in the end x is an expression in terms of y, and I'm on my way there. Okay, so now we're going to take square root. And in algebra, I have to always remind anyone, in algebra, anytime that we are taking square root on both sides, we have to leave x here equals plus and minus square root of y over 8. That's what it is, plus and minus square root of y over 8. That means we're going to run into two separate expressions. But then, so the positive square root of y over 8 is this one, and the negative square root of y over 8 is the other one. Which one are we not going to choose? See, it looks like we're going to have to go with the positive one. Okay, because here we are looking at, so in a way we already drew our picture right here, then we are going to look at the positive side, because our picture here, our region is on the right hand side of the y-axis. So we're going to choose, for now, we're going to choose a positive. Okay, but as a matter of fact, here allow me to branch out to my other side of the board and talk a little bit. So it completely depends on the picture over here, but even if we accidentally shade, because the description of the problem, all we need now is that we have the curve y equals 8x squared, and the line y equals 1 is here, and the line y equals 3 is here. And we want the area between the curve and the y-axis. We could have also chosen that. The problem itself, according to the wording description of the problem, it was just me, I chose the right-hand side. That's one part we can choose, and there's not really a particular reason that the positive side is more convenient than the negative side. Okay, so all I'm saying is the description in a problem did not really specify which side, because just simply the area between the boundary between the y-axis, the curve, and the two lines here, that it could be the right hand side between the y-axis and the curve, or the left hand side, because the curve itself from the beginning was a symmetric curve like that. So my point again is we could have also chosen this area. Okay, that means consequently your expression could have been negative square root of y over 8, and it will not change your answer. I guarantee it will not change the answer, because later on, now back into my first board right here. So now let's say, assuming we're going with this route right here, where we're taking the positive expression of the function of y, then how will that help us into the area formula? So the area now is going to be pi times a positive square root of y over 8. But then we square Okay, and so that square right there is going to get rid of the square root, and even if we had a minus sign, it's also going to get rid of that. And so now our final expression for area in terms of y variable here is going to be a pi times y over 8. Okay, so allow me to again quickly swing by to the other board and set. So even if we chose our area, our piece of the area on the on the left hand side of the y-axis, and expressing our curve here, that at least that portion of the curve here of the boundary as an x, or at least express our height here as x equals negative square root of y over 8, for example, then when we get into the area, because remember in the end we're going to rotate that each stripe right here to get a circular disk. That's when we're looking down right there, then we're going to see that disk right there. So in that way, area is going to be pi r square, which is again pi times minus square root of 8 of y over 8 r square. And so just like that, it's all going to become just pi times y over 8. And this answer and the other answer that I have arrived is exactly the same. Okay, so we definitely have to sketch the graph so that we can, make a good decision right there. And sometimes either decision is not going to change because we can feel more confidence because we have the graph there, and the graph helps us decide the problem and help us being in control of the situation right there. Okay, and so now this is the area of the cross section and completely expressed in terms of y. And it's already square right there, and it's in terms of y. And so now making it consistent with this dy expression. Okay, and so now allow me to, so I'm running short of space, so I'm going to erase this minor information, this deriving work right here. And I am going to put my cross-section area into the formula. So we found any information, we're filling it in at the same time, at the same instance. So now I'm looking at pi times radius squared, which is a positive square root of y over 8 r squared. Okay, and so now that's how, so we further found more, and we further complete our, we keep completing and getting more and more information completed here. So now in the next step, we're going to need to find out where we start our the accumulation of the disk, and where we're ending the accumulation. Where will the accumulation start and where will the accumulation end? So look right here in the picture. Doesn't matter which picture that we're rotating, either we're rotating the right region piece of area or the left region piece of area or the left piece of the area in that region right here, but we're accumulating from in the way how this picture is looking. We have to always look at the picture when we're doing these problems. Okay, these are volumes or area problems. So in the way how our picture is looking, then I have explained at the end of my video lecture, my general video discussion there, then we set for ourselves into a convention that we're gonna be, when the picture is standing up like this, then we're gonna be accumulating from the bottom up right here. Think about we're stacking up the disks. Think about the accumulation here is we're stacking up disks. Small disks, and those disks get bigger and bigger, but we're stacking up the disks. That's how we get the complete cumulative volume right there. All right, and so now that means from that understanding, then start gonna have to be the low end, and the low end here is outlined, and the picture is making it a little too much, but the low end here is y equals 1, and the upper end right here, which is the ending of our accumulation, that is y equals 3 right there. So that means now we have a clear and complete setup right here. We're accumulating from 1 to 3, and that is our complete setup of the integral. Okay, and this integral here is, in other words, ready for action, ready for us to find the final answer. Okay, and so in my next step, I am going to go ahead and cancel out the square root with that square right there, and I will also bring out that the constant coefficient pi in front. So I'm looking at pi times the integral from 1 to 3 of the y over 8 dy, and as a matter of fact, I can also pull out that 8 in front, so it should have been, so I should have done pi over 8, okay, times the integral from 1 to 3 of y multiplied with dy. Okay, and so now this integral is surprisingly simple that I don't even need to swing to the other board of mine to get the step completed. So at this point, of course, anyone doing this kind of problem must have already learned about the fundamental theorem of calculus and must have known what an antiderivative is. Okay, so fundamental theorem of calculus says in order to calculate this definite integral, we're going to first find the antiderivative of that. So it's going to be pi over 8 times 1/2 y squared. And then from where that antiderivative is, we are going to be in the next step evaluate that antiderivative from 1 to 3. Okay, and so now I am going to, in the next step, I'm going to evaluate these two integral limits into our current antiderivative. So, and by the way, pi over 8 times 1/2 is going to be a pi over 16. So I'm looking at a pi over 16, but multiply with 3 squared, and minus pi, and I wrote 12 here for some reason. Okay, it's supposedly 16, and pi over 16 multiply with 1 all squared. So now my answer is going to be simply, okay, 2 pi over 16, which is simply a pi over 8. Actually, I'm doing a miscalculation. My final answer here should be an 8 pi over 16, which reduces down to only a pi over 2. All right, that's how we get the problem done over here. So again, just like how I mentioned it at the end of the general video lecture that has all of that comprehensive detail right here. Yes, we are doing an integral problem, but this problem here is meant or is intended to be an integral that gives us a volume. So a checkpoint here that we can always check for consistency right here. The answer must always be positive because we want an actual volume. And here we go. I knew that I got a positive answer. So that's a good thing. But of course, anyone viewing the video, you must please forgive me in case I made any silly algebra error here in terms of substituting values in and do the calculation. And that's also an experience that any one of you have to carry on, like that when you're doing these kind of problems, then are we getting the correct? So now we know we had a positive answer, but are we getting the correct final positive answer? You got to double check or even triple check your calculation work right here, including from the step taking the antiderivative, and then next to the step where we're substituting values in. Okay, and that's how we're done with this problem right here. So the experience we've learned here is that, so the curve is given however it is, y equals 8x squared, even though it was given at start being whatever that was, but because we recognized the way how the solid is given right here, and that solid came from rotating around the y-axis. So that's consequently led us to concluding that. So we trace out all of these information simply based on the way how the problem described the solid like that. Okay, so the thickness on each disk has to be a dy, and that's the reason why we had to rewrite our curve here as a function of y. Okay, and once we've had that, then in the end it's an integral completely in terms of the y variable. Okay, the variable that's consistent with the y-axis right there. And then these are all the values that are relative to the y-axis. Okay.